Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome to the Deep Dive. We're here to unpack some, well, pretty complex stuff and hopefully make it genuinely fascinating. Now, if you're working on your private pilot license, you've spent hours, right, learning the basics of aerodynamics, lift, drag, how air flows at those, familiar slower speeds. You probably think of air as this nice, predictable, ideal fluid. But what happens when you really push the speed? When things get fast enough that the air itself seems to change its behavior completely? Today, we're going to take those lift and drag concepts, and add a whole new layer, a sometimes really counterintuitive dimension. This deep dive is all about the incredible and sometimes kind of wild world of high-speed aerodynamics.
Yeah, and our mission here really is to show you how air behaves differently at higher speeds. We'll introduce some critical new limits, new boundaries you might not have thought about, and we'll explore the really ingenious ways aircraft are designed to handle these challenges. To master them, actually. It's a glimpse into the physics that lets jets soar and honestly what it means for any pilot to really get their aircraft, no matter what you're flying today.
Okay, let's unpack this then. In basic aerodynamics, like we learn early on, we often treat air as ideal. Incompressible, like water, negligible viscosity, that sort of thing. But, what happens when you start going really fast? Does air just suddenly get complicated?
That's a perfect way to put it, and it really gets to the heart of this shift. What's interesting is at speeds maybe below 260 knots or so, that incompressible idea works surprisingly well. Air does act a lot like water in that regime. But as you speed up, especially as you start nudging towards the speed of sound, air's true nature comes out. It is compressible, its density can change dramatically around the plane, and it is viscous, it's sticky. And that changes everything. Lift, drag, the works.
Okay, here's where it gets really interesting for me. So even if I'm flying along, say, well below the speed of sound overall, like 400 knots, you're saying bits of my aircraft, maybe over the top curve of the wing where air speeds up, that airflow can actually go supersonic. You can have subsonic and supersonic flow happening on the same plane at the same time. That sounds wild.
That's precisely right. It is wild, but it's fundamental to this. And this brings up a really important point. When the airflow over any part of the aircraft first hits Mach 1.0, usually over that spot with the biggest curve on the wing, that speed, the aircraft speed when that first happens, is called the critical Mach number, or Mach crit. And it's not just a number, it's like this invisible boundary. It marks the edge between subsonic and transonic flight. And right there, those effects we usually ignore, like compressibility, they suddenly become very real. That's where you start seeing things like shock waves, maybe buffet, control issues.
Okay, so if the air itself is changing its behavior so much, I guess we can't just rely on our good old airspeed indicator in knots, can we? How do we even talk about speed and define these different flight regimes when things get this complex?
That's a key question, and it connects straight to the bigger picture. Because you see, the speed of sound itself isn't constant, it changes, mostly with temperature. So down at sea level, standard day, maybe 15 Celsius, sound travels at about 661 knots. But climb up to, say, 40,000 feet, it's freezing up there, maybe minus 55 Celsius. The speed of sound drops to just 574 knots. Big difference, right?
Yeah.
And that's why we use Mach number for high-speed, high-altitude flight. It's just the ratio. Your true airspeed divided by the local speed of sound. It gives you a consistent yardstick relative to how the air is behaving right there, right then.
Right, okay. And based on that Mach number, we get these different speed ranges. You've got subsonic, which is below Mach 0.75 generally.
Yeah.
Then transonic Mach 0.75 up to about 1.20. That sounds like the really tricky zone you mentioned. Then supersonic Mach 1.20 to 500. And hypersonic is anything above Mach 5, which is just incredibly fast. Most airliners we fly on, they cruise somewhere in that upper subsonic or low transonic range, like Mach 0.7 to 0.9.
Yes, exactly. And that tricky transonic range, typically just a bit above Mach crit, maybe 5 to 10% faster, that's where you hit something called drag divergence. Think of it like hitting aerodynamic mud. Suddenly, drag increases incredibly sharply, just skyrockets. At the same time, your controls might feel less effective. The aircraft could start to shake or buffet. Stability changes. To push past that point, to go even faster, requires a huge, disproportionate amount of thrust. It's really inefficient and potentially unsafe without specific design features.
Which leads us right into those limiting speeds you see on jets, VMO and MMO. VMO, that's in knots, calibrated airspeed, right?
Yeah.
KCAS. And it's mostly about structural loads, flutter, that kind of thing, especially lower down. But then MMO is a Mach number, and that takes over higher up to handle these compressibility effects we're talking about, flutter too. So the key thing is, while your airspeed indicator shows KCAS, your actual speed relative to the sound barrier is changing loads with altitude, which is why jets need MMO.
You've got it. Let's use an example, maybe an early jet. It might have a VMO of, say, 306 knots KCAS. That limit applies up to maybe 31,000 feet, flight level 310. Now, at FL 310, maybe Mach 0.82 happens to equal 306 KCAS. They meet. But here's the kicker. Climb above 31,000 feet. Now, that same Mach 0.82 limit equals a KCAS less than 306. Maybe at FL 380, Mach 0.82 is only, say, 261 KCAS. So even though VMO is technically higher, MMO becomes the actual speed limit. And sticking to these limits, VMO and MMO, whichever is lower at your altitude, is absolutely critical. Ignoring them. That's how you get into really bad situations. Things like Mach tuck, where the nose just pitches down hard on its own, or even aileron reversal. Imagine turning the yoke left and the plane banks right. Serious stuff.
Wow. Yeah, this whole Mach versus airspeed thing, especially how it shifts with altitude, it's definitely a head scratcher compared to basic flying. What to you is the most paradoxical part of all this?
Oh, there's a great one for jet transports. Picture a big jet, maybe 550,000 pounds. Down at sea level, let's say it stalls at 152 KCAS. Okay, at sea level, 152 KCAS is also 152 knots true airspeed, KTS. And that works out to about Mach 0.23. Pretty slow, Mach-wise. Now take that same jet, same weight, climb it up to FL 380, 38,000 feet. Guess what? It still stalls at roughly 152 KCAS. Your indicated stall speed barely changes. But at that altitude, because the air is so thin, 152 KCAS now means your true airspeed is way higher, maybe 257 KCAS. And your Mach number, it's jumped up to 0.50. So the indicated stall speed stays the same, but your true speed and your Mach number at the stall have increased dramatically. It's all because air density and the speed of sound have decreased so much up there. Same dynamic pressure, totally different speed reality.
Okay, so following that logic, if a pilot is climbing and decides to hold a constant Mach number, sounds like a standard jet climb technique, what happens to their indicated airspeed? My gut says it should stay the same if the Mach number is constant, but your example makes me think, no.
Your gut is leading you down the low altitude path. The key thing, the really important takeaway, is that in a constant Mach climb, your KCAS and therefore your KAS, your indicated airspeed actually decreases. It falls off. As you climb higher, the air gets colder. We already said that makes the local speed of sound decrease. Well, Mach number is your true speed divided by that local speed of sound. If the denominator, speed of sound, is decreasing and you want to keep the ratio Mach number constant, then your numerator, true airspeed, must also decrease. And if your true airspeed is decreasing while density is also dropping, your indicated airspeed goes down too. So climbing at, say, Mach 0.82 from sea level up to 38,000 feet, your KCAS might drop from well over 500 knots down to maybe 261 knots. It's a huge change on the gauge.
That is a massive drop. And that leads us, I think, to this really vivid, maybe slightly scary concept for jet pilots. The coffin corner. Sounds bad.
It is a very descriptive term, and yeah, it represents a potentially bad situation. If an aircraft keeps climbing high enough, holding that constant Mach number, its decreasing indicated airspeed, the one falling off on the gauge, could eventually get dangerously close to its stall speed, that 122 KCAS we talked about. At some critical altitude, the aircraft's stall speed in terms of Mach number, the low speed buffet boundary, can actually meet its maximum operating Mach number, MMO, the high speed buffet boundary. When those two speeds converge, you're basically trapped. You're in the coffin corner. The pilot has almost no maneuvering margin. Slow down, you risk stalling. Speed up, you risk exceeding MMO and getting a high speed buffet or Mach tuck. It's an area of the flight envelope with extremely limited options, hence the ominous name.
Okay, let's zoom right in on the wing surface itself. Get down to the nitty-gritty. Tell us about this boundary layer. Sounds like this thin, invisible layer of air right on the skin.
That's a good way to picture it. It's this super thin layer of air directly touching the wing's surface. Because air is viscous, it has that stickiness. This layer gets slowed down or even stopped completely right at the surface. This creates skin friction drag. Now, this layer usually starts off smooth, behaving nicely. We call that laminar flow. Less drag, which is great, but it's also kind of unstable, easily disturbed, like a perfectly smooth sheet of water. Further back on the wing, it almost always transitions to turbulent flow. Think more like a choppy river. The flow is messier, creates more skin friction drag, but it's actually more stable. It hangs onto the wing better. So for designers, a big goal is always to try and keep that efficient laminar flow going for as long as possible along the wing chord.
And then there's separation, which sounds like exactly what you don't want. Like the air just gives up and peels off the wing.
Exactly. That's precisely what it is. Separation is when the airflow, usually after it's become turbulent, can no longer follow the curve of the airfoil and it breaks away. When that happens, you get a massive increase in drag, formed drag, and crucially, you lose lift, a lot of lift. As you increase the angle of attack, the AOA, that separation point, tends to creep forward from the trailing edge. Stall is basically when separation covers too much of the wing. This is also where you see those little fins on jet wings' vortex generators. They stick up into the faster air above the boundary layer and create tiny swirls, vortices, that pull that high-energy air down into the slow-moving boundary layer right near the surface. This re-energizes the boundary layer, helps it stick longer, delays separation, and really importantly in transonic flight, it helps prevent shock waves from causing separation.
Right, shock waves, you've mentioned them a few times. What exactly are they? Why are they such a huge deal for high-speed flight? Is it like hitting some kind of invisible wall?
That invisible wall analogy isn't bad for capturing the effect. Think about it. When you're flying slower than sound, the air ahead gets a pressure warning that you're coming and it smoothly moves aside. But when you reach the speed of sound, your aircraft is basically keeping up with its own pressure waves. There's no warning time. The air particles literally can't get out of the way fast enough. They pile up, compress violently. This causes sudden, drastic, almost instantaneous jumps in pressure, temperature, and density, and a sharp drop in velocity. That abrupt boundary between the undisturbed air ahead and this compressed, chaotic region behind, that is a shock wave. It forms whenever supersonic flow is forced to slow down to subsonic abruptly.
So these specifically pop up where the air flowing over the wing goes supersonic, then has to slow back down again.
Yes, precisely. Particularly where the airflow accelerates over that curved upper surface to Mach 1 or faster, and then has to decelerate, often past the point of maximum thickness or curvature. When a shock wave forms standing straight up, perpendicular to the flow, we call that a normal shock wave. It's like the air hitting that brick wall you imagined. The flow immediately behind it slams down to subsonic speed. Static pressure and density shoot way up, and a lot of the air's energy is just lost, converted mostly to heat.
And these cause more problems than just that massive drag increase you mentioned earlier.
Oh, absolutely. The drag increase, the wave drag is significant, especially once you're maybe 10% above Mach crit. It really ramps up. But arguably more critical are the other effects. The shock wave disrupts the boundary layer behind it, causing massive airflow separation. This separation leads directly to Mach buffet, that heavy vibration or shaking of the airframe. It also messes with the wing's pressure distribution, causing changes in trim and stability, like Mach tuck, where the center of pressure shifts aft suddenly, making the nose pitch down strongly. And it can significantly reduce how effective your control surfaces are, makes the plane harder, sometimes much harder, to control. That's why understanding and avoiding these effects is paramount.
Okay, wow. Given all these really complex and frankly hazardous challenges, how do aircraft designers actually overcome them? How do they make high-speed flight possible, let alone safe and routine?
Well, one of the most fundamental design solutions is wing sweep back. Sweeping the wings back. The thinking behind it is actually quite elegant. It relies on the fact that only the airflow component flowing directly perpendicular to the wing's leading edge matters for creating the pressure distribution and triggering those shock waves. By sweeping the wing back, the effective chordwise flow component, the bit perpendicular to the leading edge, is slower than the actual speed of the aircraft through the air. So the wing essentially thinks it's sighing slower than it is. This delays the onset of compressibility effects, pushes Mach crit to a higher speed, and makes that drag rise much more gradual.
Ah, clever. But I feel like there's always a trade-off in aerodynamics. Isn't there a downside to swept wings? Something about stalling at the tips first, tip stalls.
Indeed, there is a significant downside. Highly swept wings have this tendency to stall out at the wingtips before the wing root near the fuselage. It happens because that boundary layer air we talked about tends to flow outwards along the span of a swept wing towards the tips. It thickens and separates there first. Now, because the tips of a swept wing are far behind the aircraft's center of gravity and contribute significantly to lift back there, when they stall, the overall center of lift shifts forward abruptly. This makes the nose pitch up, which deepens the stall. It's an unstable stall characteristic. And this can be particularly nasty with T-tail designs, where the horizontal tail is high out of the wing's disturbed air, so it stays effective and can allow the pilot to unknowingly pull into an even deeper stall.
And that's why we have safety systems like stick shakers and stick pushers on these types of aircraft to catch that before it gets really bad.
Exactly that. That T-tail issue is a big part of it. The tail stays flying, basically, even when the wing is stalling. So A stick shaker gives the pilot a physical warning. It literally shakes the control column, usually starting about 5 to 7% above the actual stall speed. Wake-up call. A stick pusher is even more proactive. It's an automatic system that, if the AOA gets too high, maybe 1 knot above stall speed, physically pushes the control column forward. It forces the nose down to reduce the AOA and prevent the stall from fully developing. Some even have G-limiters built in. They're crucial safety nets for these flight regimes.
Okay, so how about the flight controls themselves? Moving those surfaces at high speed must be totally different from, my Cessna with cables and pulleys.
Oh, completely different world. High-speed aircraft obviously have the primary controls, ailerons, elevator, rudder, but they also rely heavily on secondary or auxiliary controls. Things like flaps, slats, spoilers, and trim systems. Spoilers are a great example. Those panels on top of the wing, they can pop up to spoil the lift, acting as speed brakes in flight or helping braking on the ground, or they often work together with the ailerons for roll control. In fact, many jets have 2 sets of ailerons. Small inboard ones for high speeds where you need precise control but less deflection, and larger outboard ones for low speeds. The outboards often get locked out when flaps are up.
And flaps and trim. I look at a jet wing and the flaps look way more complicated than the simple ones I use. And the leading edge looks sharp.
You're right, they are much more complex. High-speed wings often need sharp leading edges for efficiency at cruise. But sharp leading edges stall easily at low speeds. So, to get good low-speed performance for takeoff and landing, they use very sophisticated systems. Often multi-segment flaps on the trailing edge, and powerful leading-edge devices like slats, which are basically small airfoils that move out from the leading edge, or cougar flaps that fold out from underneath. These create slots, energize the airflow over the top, delay separation massively, and allow for much higher angles of attack and lift at low speeds. They can cut the stall speed dramatically.
And pitch control. It's not just the elevator back there doing all the work, is it? Seems like jets need something more powerful for trim.
Good observation. Jet transports operate over huge ranges of speed, altitude, and center of gravity. This means they need really powerful pitch trim, much more than a little trim tab can provide. So they use what's called a variable incidence horizontal stabilizer, or sometimes a trimmable horizontal stabilizer. The entire horizontal tail surface pivots up and down. This is commanded by the trim controls. It takes care of the main balancing act, trimming out the large pitching forces, leaving the smaller elevator free for the moment-to-moment pitch control inputs from the pilot. It's much more authoritative.
And finally, just physically moving these huge control surfaces against the air loads at hundreds of knots, it must take enormous force, right? No way a pilot could do that directly.
No way at all. You're absolutely right. The aerodynamic forces are immense. So control surfaces on these aircraft are moved by hydraulic or sometimes electric power actuators, power control units, or PCUs. The pilot's yoke or rudder pedals just send signals to these powerful units, telling them what angle to move the surface to. The PCU does the heavy lifting. Some systems might have manual reversion with aerodynamic tabs as a backup if the power fails, but it's usually much heavier and less effective. The power is essential.
We've circled back to Mach a few times. It sounds like the plane is just shaking itself, what's really causing it deep down. And you mentioned different kinds.
Right. Fundamentally, Mach buffet happens because of airflow separation on the wing, usually induced by shock waves. It's about the local airflow speed over the wing reaching critical speeds, not necessarily just the aircraft's speed itself. It happens anytime you ask the wing to produce too much lift for the current conditions, pushing that local flow into the transonic trouble zone. So you definitely have high-speed Mach buffet that happens when you fly too fast, exceeding the MMO limit. Shock waves form, cause separation, and shake. But, and this is the really interesting part, you could also get low-speed Mach buffet.
Low-speed Mach buffet, okay, that still sounds completely backwards. How can you get something called Mach buffet when you're flying slow?
Yeah, it is counterintuitive. But think about it. It happens when you're flying too slow for your current weight and altitude. To generate enough lift in thin air, or when heavy, you need a really high angle of attack, right? Well, that very high AOA forces the air to accelerate massively as it goes over the wing's upper surface. So much so that even if the aircraft is at a low indicated airspeed, the local airflow over the wing can still reach sonic speeds, form those same shock waves, cause separation, and produce the exact same buffet you'd get at high speeds near MMO. Your wing thinks it's going fast, even if the airplane isn't.
So it really boils down to angle of attack, AOA. That's the real driver here. Not just the speed shown on the airspeed indicator, but how hard the wing is working relative to the airflow.
That is absolutely the critical takeaway. Angle of attack has the biggest influence on triggering Mach buffet, whether it's at the high-speed boundary near MMO or the low-speed boundary near the stall. Anything that forces you to use a higher AOA increases the risk. So things like high altitudes, thinner air means you need more AOA for the same lift. Heavy weights again, more lift needed, higher AOA. And high G-loading points and turns, turbulence encounters, even abrupt control inputs. They all effectively increase the wing's loading and demand a higher AOA, pushing you closer to that buffet boundary, high or low. It's all connected through AOA.
Wow, okay. So this whole deep dive really hammers home that high-speed flight isn't just, going faster in the way we learn initially. It's a completely different aerodynamic environment, different physics, different challenges, and really clever engineering needed to make it work safely. My little trainer definitely doesn't have a coffin corner, thankfully.
Exactly. And connecting this back for you, as someone learning to fly, even if you never plan on flying jets, understanding these principles gives you such a deeper appreciation for flight itself. It shows how aircraft design is this constant evolution, this balancing act, to master how air behaves across this huge range of speeds, from takeoff roll to high-altitude cruise. It highlights how every curve, every sweep angle, every little device on a wing is there for a reason, often dealing with physics far beyond basic lift and drag.
It's definitely a solid reminder that even when you think you've got a handle on how air works, it can always throw you a curveball, especially when you start pushing the boundaries of speed or altitude. It really is a dance between physics and design.
Which maybe raises one last thought. As you continue your own flying journey, and you look at different aircraft designs, maybe even comparing different trainers or looking at light twins, how might some of these high-speed principles, things like compressibility or boundary layer behavior, even subtly influence the design choices and flight characteristics you see at lower speeds? What clues might be hidden in plain sight about managing the air, even when you're not anywhere near Mach 1? Something to think about next time you're pre-flighting.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.